Hi, recording. I'm just starting. So, let me try again. A functional group is a group of atoms on a molecule that react in a characteristic way. So, this is going to be one of the most important skills for you to learn for the rest of the course. Because otherwise, we're going to give you molecules and it's just going to be like big overwhelm. What do? And when we have functional groups, we can say, I see this thing is an alcohol. This thing is a ketone. And we can get information about the reactivity from that. So that is why functional groups are important, and we'll kind of talk a little bit more about that in a minute. To start off, this is going to be what you have to memorize in terms of the names. So this box right here. And to try to help you memorize it, I'm going to talk a little bit about some of the things and some little mnemonics. And then I've also kind of tried to organize them and divide them into families that make them a little bit easier to memorize and to learn. So let's start off with the first family, the hydrocarbons. So first up, we have alkanes. And you'll notice that alkanes are not highlighted, and it's kind of confusingly because alkanes are not a functional group. Alkanes are kind of like the absence of a functional group because alkanes don't really react. These are compounds that only have carbon-hydrogen single bonds. So we call them alkanes, and they're kind of our basis of comparison for everything. Now, if we have a carbon-carbon double bond, she is now reactive, and this is an alkene. And similarly, if we have a triple bond, it's called now an alkyne. So these you would want to circle and label as a functional group. And the nice thing about this of like single bonds A, double bonds E, triple bonds Y, is it goes in ABC order. So that's kind of a nice trend. Finally, if we have a bunch of like carbon double bonds in a ring, we call that an arene ring. You might also hear it called an aromatic ring. I like arene because it's shorter, but both of them work. Now, you might be asking, what is R? So R stands for any alkyl group, or any kind of like alkane-like thing. So for example, this double bond, I'm saying that the things attached to the double bonds can be carbon things or hydrogen things. So for example, this with just hydrogens is an alkene, like this, that's fine. And also, another thing that's an alkene is something that has a bunch of carbons and then some hydrogens. Or an alkene could have a hydrogen, carbon, hydrogen, carbon, 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 crazy, 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 crazy. This is also an alkene. And this, we can just represent this whole thing as an R group. And again, it's just kind of short for like anything that we don't care about or something that's not important. We can use R to specify a specific thing. Like I could say, actually for this example, R is going to be this, and it has like other things, and it's like a complicated whatever. But if you don't see a rule that says R says something, assume that it's like a little methyl or an ethyl or like an alkyl chain of some sort, just hydrocarbons. Questions on the hydrocarbon family? Yeah. So a benzene ring is a type of arene ring, but benzene is a singular molecule, whereas this is if you have this on a bigger molecule. We call it an arene ring. Yeah, go ahead.
Is it always like a hexagon, or is it
You could do a 5-membered ring. Like this would work. But again, we're not going to get in the nitty-gritty. We will typically present it as the 6-membered ring. And you just need to know functional group-wise, it's an arene ring. If you give it a specific name, you would call it like a benzene ring or a phenyl ring. But like, again, we're on functional group land. So the next family are the heteroatoms, which I affectionately call the oxygen mafia. So basically, all of these are kind of related to oxygen. And the kind of classic like dawn of the mafia here is the alcohol. So the alcohol is any kind of alkyl chain, and then you pop an OH on it. So it could look like that, it could look like that. And the alcohol's cousin is a thiol. And remember on the periodic table you have O and then S is right under it. So SH, it just looks like OH. And I like to think in the mafia, the thiol gets rid of problems and is like, shh, and like tries to make problems disappear. It's dumb, but here we are. So if we have an oxygen that's attached to a carbon thing on one side and a carbon thing on the other side, and they don't have to be the same, we call that an ether. And I like to think like either or, you can go either way, and it's a carbon. Yeah. Now, if you're attached to carbons on both sides, and then those carbons are attached to each other and make a little three-membered ring, she's an epoxide. Then down over here, we have nitrogens that are attached to things, are called amines. And it's going to be attached to three things, but those things could be carbon things or they could be hydrogens. So this is an amine. This is amine. This is an amine. That is an amine. Last one is if we put a halogen on something, we call it an alkyl halide. Now, these two are the twins that like to parent trap and switch out and confuse a lot of people on exams. I'll get in 1 second. So for these two, we're going to start off with an acetal. So let's look here. We know the R group is going to be a carbon thing. So if I have an oxygen attached to carbons on each side, what functional group does that look like that we've already talked about? The ether, right? Carbons on both sides. So here we had an ether, and we also have an ether right here. But when those ethers are attached to the same carbon, it is now an acetal. And if you were to call this just an ether or even two ethers, that would be incorrect. The reason why that would be incorrect is because this thing reacts very differently from an ether. And it has to do with this being bonded to two oxygens versus just being bonded to one oxygen. So that is why this is a separate functional group. And the acetal is the kind of dominant label there. And then closely related is the hemiacetal. So hemi, think like halfway there. We do have one kind of little subordinate ether, but then we only have an OH. We have like an alcohol instead of another ether. So this is going to be the hemiacetal, kind of halfway to the acetal. Question? Mm-hmm. Specifically carbons. Carbon, or it could be a hydrogen.
And is that the same for all the other?
Correct.
They
Correct.
have to be either carbon or hydrogen.
For all of these, we are assuming that they are a carbon.
Okay.
And then that carbon can be a long carbon chain, but the first thing that it's connected to is a carbon.
Okay. So could you write, could you substitute the R's for C's?
Totally. I'm giving you the most general version of it, and like then you can be like, oh, okay, this is an epoxide. Or you could do, this is an epoxide. Like you can draw a billion epoxides. I'm just giving you the general form.
Okay, so just for heteroatoms, the R's are C's.
For all of them.
Okay.
Yeah. Yep.
So when we're identifying the functional groups, even though it's an ether from that, the correct one would be the
Acetal.
this one.
Yeah, the kind of, the ethers are components of it, but it reacts as an acetal. It doesn't react as an ether. And the whole purpose of these is to figure out how parts of molecules react. Names? Danny, Tommy. Cool. Last family, I'm going to do one more like introduction here, and then we're going to have you all do some practice, and then I'll answer a bunch of kind of specific questions, okay? So the last family here is the carbonyl compounds. So a carbonyl is a CO double bond, and a carbonyl is an umbrella term. Now this is going to be our first call and response of the day, and it actually isn't really a call and response, it's just a chant. I want us to say a couple times, a carbonyl is an umbrella term. A carbonyl is an umbrella term. A carbonyl is an umbrella term. Great. So if I asked you to name the specific functional group name for something, you should never put a carbonyl, because it's not specific, it's an umbrella term. So we have a bunch of different flavors of carbonyls that change depending on what it's next to.
So it's like never the answer.
Carbonyl will never be the answer. For, like, you will have a test question that looks just like this, where we put a molecule up and say circle 8 functional groups. And if you write carbonyl, you will not get points.
And do you always tell us
I think. I'm not sure. So, carbonyl, and then let's start off with kind of the boring ones. So these ones are the ones that you see a lot in like bio classes. So if carbonyl has carbons on both sides, then we call it a ketone. It's kind of in the middle of this carbon chain. And then if it has on one side of it a hydrogen, and then the other side probably a carbon chain, or you could have this like special case where they're both hydrogens. We call this an aldehyde. And the kind of mnemonic from biology for remembering which one's which is because this has an H, it's always going to be on the end of a chain. And so we say aldehydes can't hide. Like they were never going to blend in, whereas the ketones like to blend in the middle of the molecule. Then we have, okay, what if we put an alcohol next to a carbonyl? That's a carboxylic acid. What if we put an ether next to a carbonyl? So this is like carbon-carbon connected to the oxygen ether, but carbonyl, she's our good friend Esther. If we have a carbonyl and we put an amine next to it, it becomes an amide. And then a carbonyl with a chloride next to it is an acid chloride. So I've tried to kind of like set this up so that there are some patterns that you'll kind of see. I've tried to highlight them similarly. But similarly to what we said with the acetal, if you circled this and called it an amine, it would be marked incorrect because this reacts as one functional group. Now, why does something like this react as one functional group? What's the answer to 95% of the questions in this class? Resonance. Can this do resonance? Yeah. This has a resonance structure over here that looks like we have a double bond OH plus here and O minus. So this is not reacting like an alcohol and a carbonyl separately. This is one reactive unit. And that's why you can't do the subordinate names. You have to do the kind of overarching name. I'm going to say one note here, and this is something that you are not tested on, but you will see it come up in lectures 3 and 5, and so I want to preview it for a quick second. We've already kind of seen the idea of like these functional groups, smaller things coming together and making a bigger thing. And there are even more that we haven't told you about yet. So like one is, what if you have a ketone and an alkene? She becomes an enone. And you're going to do some reactions with enones in lecture 3 on Tuesday. You also have like, what if you have an alkene and an alcohol? That's an enol. And like we're going to do a lot with that in lecture 10. And so just know that there will be more functional groups eventually, but the only ones that we are going to test you on for the first exam are these. There are even some additional ones in the problem set that you'll see, like a thioether, which is like the sulfur version of an ether. These are the ones that we are going to test you on. Lastly, this is not a compound functional group. And it's not a compound functional group because what's the hybridization of this carbon? sp3. So it has 2 hydrogens that are hidden there. All of these, like 4 electron domains, sp3. And can sp3 atoms delocalize? No, because they have to have a p orbital. So that means these can't do resonance with this because they have something in the middle that can't delocalize. And so these would be a separate alkene and a separate ketone, whereas these, when they're all together and can do resonance, are an enone, all one group. But with that, I've written 2 molecules here, and on the attendance survey, I told you, like, write this down if you're not a tablet user. And all I want you to do for this is I want you to write out, identify, circle, and label every functional group that you can. I'm going to give you a few minutes to work on it, and then we'll go over it. And then while y'all are doing that, I'll probably circulate and answer some individual questions. So. Ooh. Lonnie, and your friends will. Wait, Lonnie. Lonnie, let me see. Yeah, okay. I can do it. Like it could be one carbon, two hydrogens.
Oh.
Two carbons, one hydrogen. All hydrogens, all carbons.
Okay, thank you.
Yeah, okay.
Thanks for asking. Wait till 9 o'clock.
I only knew because I knew I already got to Daniel, and I remember when we were like sitting on the same thing. First letter?
You already said it in that previous sentence, right? There are two then.
Oh, you said G. I heard T. Sure. Okay, so I was just really, we're both in bed, but you're in I. You don't really know what this is? Oh my god, the E's! You already found the E.
We are in a function group.
Wow, you're functional group only. Yes.
I'm pretty confused.
Name?
I'm done.
Sorry, do you lose this one? It's okay to not.
Yeah, 3 inches, so that's an Oh, wait. Cause there's the one, and then. Oh, and I just put mine. Yes, because look. Yes. No. That was. Oh. This is fun. Can Austin?
So.
Okay. So let's see how you did on this practice problem. Okay, it's kind of written sloppily, but how did you do? Check yourself.
The first one is all I got done.
Okay. No, that's totally fine. I didn't give you enough time. Yeah. Of the ones that you have done, how did you do? And specifically, if you wrote something different than me, ask me about it because someone else probably did the same.
Can we go over amine,
This one here, Amin.
the other one, the HN variable?
This one, I mean.
Yeah, can we just go over it?
Yeah, so it's a nitrogen that's attached to three things, and those three things could be carbons or hydrogens.
Okay.
So here, in this case, it's 2 carbons and 1 hydrogen, still an amine.
Do we need to color it all?
Not necessarily. Like, I mean, it should be pretty clear what you're doing. Like, if you want to be really precise and do this, sure.
Or it doesn't really like not nitpicky with that?
No. I think it's more nitpicky with like an ether versus an alcohol, where like you want to show that this has a carbon on either side, because that's the kind of thing you're looking for. Yeah. Yeah. Melanie.
Do you have to say like upper fluoride or it's fine, just leave it as
I think we would give you credit for alkyl halide. And like alkyl fluoride here is a more specific name, and so that would be even better. But we like to call the whole family the alkyl halides. Yeah. Yeah. I mean, my tip is look for anything that's not a carbon and then try to figure out what it is. So, like, if I just circle the things that were not carbons, that's getting like 90% of these, and then we just have to classify them. Yeah.
We did, yeah, why is the an amine and a ketone not an amide?
Because, so this is an amide. The nitrogen has to be attached to the carbon that's on the carbonyl. Whereas here, nitrogen's attached to this, which is not the carbonyl.
Oh.
This is, again, what we said, an sp3 hybridized carbon. There's a hydrogen there. So those aren't connected. Yeah.
For the first structure, why is the oxygen after if it's not between two carbons?
Well, what does Me mean?
What is
What is
I don't
Me?
know.
So Me is short for methyl.
Okay.
So CH3. And I did that intentionally because I want y'all to get used to seeing methyls written out as either CH3, we can abbreviate with the Me, and like ethyl is ET, or I could have just drawn a line.
Yeah.
All of those are equivalent, and you should be comfortable working with all of them.
Okay, I thought that was like a separate.
Yeah, there's no Me element.
So if it was like, let's say it was an F, it wouldn't be an F. It has to be connected to.
Yes.
Okay.
And the pronunciation is not super important, but ether and amine instead of amine. 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 Like I gave someone a mean look.
I was doing the preset, and it took me so long to figure out it's not an element, and I was just like going through it periodically.
And you're like, where is she?
So I didn't know it was a serious thing.
You're totally fine. Okay, I know there are probably more questions. I know you're probably not done with it. I do need to start moving on. So, I'm gonna ask you to indulge me for another like 2.5 minutes to show you something you haven't learned yet. And I'm showing you it here. It will not be on the first exam at all. And you'll probably learn it in like lecture like 3 or 5. But it fits in really well with functional group analysis of like looking at molecules and trying to label them. So, not all carbons are created the same. Like some carbons are kind of on the end and they're connected to fewer carbons, whereas some are carbon like socialites and have a lot of carbon friends next door. And so we can classify a carbon based on how many other bonds it has to carbons. So we say if something is attached to one other carbon, it is a primary or 1' carbon. So this is a primary carbon. This is a primary carbon. This is, and so on. A carbon that's attached to 2 other carbons, we say is a secondary or 2' carbon. A carbon that's attached to 3 carbons is tertiary, so on, so on. Now, a carbon that's attached to no other carbons, we call her a methyl carbon. And it's kind of because methane, but you could also have something like CH3Br. This carbon is not attached to any other carbons, so we would say it's a methyl carbon.
Oh, yeah, never mind, that was silly.
No, you're good. So this helps us be more specific about our functional group names. So if we have an alcohol that is attached to a primary carbon, this carbon's attached to one other carbon, we would call this a primary alcohol. And similarly, this is secondary carbon, so this is secondary alcohol. Tertiary carbon, tertiary alcohol. Can we have a quaternary alcohol? No, why? this ain't Texas. We can't have a Texas carbon here. We can't have more than 8 electrons on the carbon. And if we had a carbon attached to 4 other carbons and an OH, that's 5 bonds. That's way too many. Cool. Similarly, alkyl halides are named the exact same way of primary carbon, that's a primary alkyl chloride, and so on. And this gets on your question where I actually put the name of the halide, but they're all alkyl halides. So these are really similar and go together really quite nicely. And so maybe, what type of alcohol is this? Primary, secondary, or tertiary? Lots of mumbling. Let's break it down. We look at the carbon. How many other carbons is this carbon connected to? 2. 1, 2. So this is a secondary alcohol. Then what about this one? How many carbons is this carbon connected to? 1. So it's a primary alcohol. Exactly. Now I'm going to teach you something confusing. So the other ones, for alcohols and alkyl halides, it's based on the carbon, right? Like how many other carbons that's connected to. For amines, it's about how many carbons are connected to the nitrogen. So like here, this is a primary amine because it's connected to 1 carbon, and it doesn't matter whether that's, in this case, a primary carbon or a secondary carbon or a tertiary carbon, all of those would still be a primary amine. Whereas a tertiary amine is connected to 3 carbon things. So it kind of switches up the naming here. But again, I thought it would be helpful for you to have this guide here because you do it in like 5 minutes in lecture and then it kind of washes over you and you're like, what? And it's that really similar skill of like naming molecules, of like trying to identify functional groups. So really quick, why do we do all this? Why does this matter? So let's say this is something that you're going to learn in lecture 5. Let's say I just listed out these reactions and like 50 more of them, and I could write 50 more of these. And what kind of patterns do you see about these reactions? Yeah, we see we have some carboxylic acids over here, and we already know we have some alcohols. This is another primary alcohol. So we have carboxylic acids and alcohols, and what functional group do we have in the products? Our good friend ester. You're going to be in a coffee shop one day waiting for like your latte or whatever, and you'll hear like large mocha frap for ester, and then you'll think about this. Yeah, I'm so sorry. I'm so sorry. So these are all esters. And do you see how like the functional groups are the most important things? They're kind of how the molecule is reacting, and everything else is just a side chain. Like, I mean, this just stays over here. This just stays over here. And like this just stays over here. Like those parts of the molecule aren't doing the reaction. Only these functional groups are. So instead of memorizing all of these as separate reactions and the rest of the list of 50 reactions I would give you, we teach it this way. We say any carboxylic acid, doesn't matter what this R group is, and any alcohol, it doesn't matter what this R group is, they are going to come together and form an ester. That is the power of this. It's letting you work smarter and not harder, and it's letting it become way less tedious. Does this make sense why this is going to be an important skill for you to learn and kind of get like a thumbs yes or no? Is this an important skill? Do you see the importance? Cool. Your assignment for Tuesday is to know the functional groups cold. I'm so sorry. It keeps building up speed, and it's one thing that you want to have down now, because lecture 3 is when we're going to start doing reactions with these functional groups. And if you're still having to be like, hey, carbonyl next to an OR ester, that takes up too much time. You're going to be trying to take in all the other new information. I appreciate you. We are now about to do another hard pivot, so like brace for impact. Whew. And let's talk about MO theory. Woo! So, MO theory takes us from talking about atom structure and reactivity to that of entire molecules. So there are kind of 2 big ideas that we want you to take away from it. Like yesterday he was talking about math and wave functions, and we're not going to test you on that. We don't care. Or shouldn't say that. That's quantum mechanics and other people, it's their job to care. That's not organic chemistry. So we're going to take a lot of the results from quantum mechanics and just assume that they are our facts, and they're going to be our starting point. And so I'm just going to say know these facts rather than deeply understand them, which feels kind of wrong. The rest of it you will have to deeply understand after this, but these are going to be kind of our facts where we start. So key idea number 1, the number of atomic orbitals that a molecule has is equal to the number of molecular orbitals. So we know hydrogen only has a single atomic orbital with a single like s orbital, but most all of our other atoms are going to have an s and 3 p orbitals. So in total it's going to have 4 atomic orbitals. So let's count how many atomic orbitals are in this molecule. Well, we have 7 hydrogens, so we have 7 that each have 1 atomic orbital on it. And then how many atoms do we have that have the 4 atomic orbitals? Yeah, we have 3 carbons, 1 oxygen, so we have 4 that are each supplying 4 atomic orbitals. So this is 7 and 16, 23. So we know that we have 23 atomic orbitals. So how many molecular orbitals should we have? 23, because the number of atomic orbitals equals the number of molecular orbitals. Now, when you are doing an MO diagram, this is super important, because remember you're trying to list out all the bonding and anti-bonding and non-bonding and everything, and this gets you a target number that you need to get to. So let's say I tried to list all of them out, I only got 20. This lets me know that I'm still missing 3 molecular orbitals, like I've forgotten them, they're somewhere. And it's a really great reality check, and you should be doing it on the problem set and on the exam. Let me give you one more to try to do on your own really quick. C6H6. I want you to use these formulas and calculate how many atomic orbitals that you should have. And then, Alisar. Work.
Look at that.
Wow. Did you have a question?
I did, and then I realized it was silly. I just did it.
Work.
Was the atomic orbital also depend on the resonance?
Atomic orbital is about an atom in isolation, thinking about one part. So resonance doesn't matter.
No, that doesn't matter. You can have double bonds between carbon.
But double bonds are made up of the s and p orbitals, so it doesn't matter. Okay, did you all get 30 atomic orbitals? So how many molecular orbitals should we have? 30, thank you. So that's key idea number 1. Key idea number 2 is for each bonding molecular orbital, we have an antibonding molecular orbital. So bonding orbital has to do with the in-phase overlap of these atomic orbitals, and then antibonding is out of phase. So like, remember for a p orbital, we always are going to shade in one of them for this idea of like the phase of the orbital. And for a bonding interaction where a bond is present, we are going to have them shaded in the same way. So like on the top, they're both going to be shaded in. And so we can imagine them as kind of one filled in cloud here. Whereas if it was an antibonding orbital, they would be out of phase. So one would be shaded on the top, and then it would be open on the top, and then same on the bottom, but it flipped. And this creates a node between them, which is less stable. So this is the idea of the antibonding orbital. It's like you have your p orbitals that could do a bond, but they are just overlapping in the wrong way, in the out of phase way. Now, one kind of metaphor I want to bring up here is physics and waves. I'm not going to get deep into it because I don't claim to understand physics. So do you remember this idea where if you had 2 waves, there's a certain way that you can add them together where like it's going to take these individual signals and amplify them and make it bigger? I think the term is constructive interference. But there's another way that you can add them together where if you add this, which is positive, and this, which is negative, they're going to cancel out and do destructive interference. I think about that idea when I think about bonding and antibonding orbital, whereas this would be kind of an in-phase overlap, and this would be kind of a representation of bonding in some level, and this is the out-of-phase overlap, and this would be the anti-bonding at some level. It doesn't directly correlate, but like electrons are hard things to think about because of the whole wave-particle duality. Like, I'm not going to get super into it, but it's just, in intro chemistry, we think of electrons as little particles that are in certain places. And the mathematics of quantum mechanics has shown that actually they kind of behave more like waves sometimes. And so this is kind of getting at the wave nature of it. And you don't need to understand any deeper than that. It's very general ideas. We're not going to ask you about waves or anything. You just need to know that there are bonding and anti-bonding orbitals, and you need to know how to draw them. So on that note, let's talk about drawing them. So I gave you most of these, but I want to talk about how to draw the anti-bonding and bonding orbitals when your two atoms have a different electronegativity. So here, carbon-carbon, they have the same electronegativity. They're going to be the same size orbitals. But when they have different electronegativities, on the bonding orbital, you're going to have larger lobes on the more electronegative element and smaller lobes on the less electronegative element. And so if you wanted to think of it, again, like this kind of bubble of like, hey, this is going to be in phase overlap. We're going to shade in both the tops or both the bottoms. It doesn't matter. It's kind of like, I don't know, an oblong little like bag or something where like it's more around the oxygen and less around the carbon. So for bonding interactions, larger lobes on the more electronegative element. And then for antibonding orbitals, it's the opposite. So the less electronegative element here between carbon and oxygen is carbon. So for the antibonding orbital, it's going to have larger orbitals on the carbon and smaller on the oxygen. And remember, we're going to do it out of phase here, and there's a little node. So you might be like, okay, we're learning the rules of this game that is played by molecules that are very, very small. Why do we care? So let's say that this is your pi star anti-bonding orbital, and it's empty, right? Like no electrons are in there. And a donor wants to come in and attack this pi star orbital and put electrons into the orbital. Which side do you think it's going to attack? Is it going to attack the carbon and attack this? Or is it going to attack the oxygen and attack this? Take a minute to think for yourself. If you think oxygen, raise your hand. If you think carbon, raise your hand. Okay, and a lot of indecisive in the middle. I appreciate it. So, it is going to attack carbon. And let's talk about why. So, these orbitals, remember, are empty. And so, if we're trying to put electrons into the orbital, this is simply a bigger target. And so, it's easier to put electrons into this side of the antibonding orbital because it's larger. Then, there's also a charge reason. So remember, generally in this kind of polar CO bond, the oxygen's more partial negative and the carbon's more partial positive, right? So if you're coming in with a donor, like a lone pair, you have electrons, the electrons are going to want to go towards the positive charge. And if it tried to go towards the negative charge, the partial negative over here, that partial negative would kind of push back against it because negative charges, like charges, repel. So you have both kind of a charge reason and a space reason why a donor would attack the carbon of a carbonyl. Woof. Questions? Questions on this? I know that was like a lot. Yeah. So you can't attack a pi orbital, and it's because a pi orbital is filled. A pi orbital already has electrons in it, and so like let's say you are electrons trying to enter this house. This house is already occupied. It's squatter's rights, so you can't like go and like kick out other electrons. You can only put electrons into empty spaces, and an anti-bonding orbital is an empty space. Well, remember, when there's a pi bond and an antibond. These exist at the same time. But this is filled with electrons, and this is empty. And so the only one that we could attack is the pi star. Yeah.
So you said the carbon is less electronegative. Could you explain that? Because it kind of doesn't make sense. Wouldn't the electrons prefer to go to the oxygen because the electronegativity is attractive?
So think about it this way. This carbon or this oxygen already has electrons around it. So now we're asking more electrons to approach. And in order to get to this oxygen, which you're right is more electronegative, it would have to get through this cloud of electrons around it.
Like, is it anti-bond?
But both of them exist at the same time. Like this is the space where it's going, but these are happening at the same time. And there are, in fact, like if I put these on top of each other, there is in the same breath more electrons around the oxygen, and there's more space to attack around the carbon. And having more electrons around the oxygen, in both versions of this, the oxygen is more partial negative. And so that's going to repel electrons that are trying to attack. It's tricky, it's a lot. We're going to answer more questions as we do some practice, so I'm going to move on. But one thing, if I do this, why can I not just say that the product is this? Yeah. Yes, we're going to get there, but what's wrong with this Lewis structure? This ain't Texas. It's not a Texas carbon. We can't violate that rule. So we know that we also have to break a bond when we do this. And this is where we get to the second call and response element of the day. Electrons in antibonds make the bond break. So we're going to chant that like 4 or 5 times, and we're going to do a gradient. We're going to start off quiet like it's a secret, and then we're going to get very loud, okay? So, electrons in antibonds make the bond break. We're going to do it again, a secret. Electrons in antibonds make the bond break. Now normal talking volume. Electrons in antibonds make the bond break. Now we're trying to get someone's attention across the room, but it's a small room. Electrons in antibonds make the bonds break. Now we're just so excited we can't contain it. Electrons in antibonds make the bonds break. It's silly. But if you put ever, at any point in this course, if you put electrons in an antibond, what should happen? The bond breaks. Now another question. If the bond broke, what did you do? Thank you. Thank you. This is such like a pivotal thing to like ingrain and kind of like have in your mind when you are working with MO theory, that like I'm okay with doing like cult brainwashing as long as you know this fact, you know? And so, yes, this is the first of many call and response chants that we will do in section, which I know is so much. Welcome. Last thing, so relative energies. I like to think of it as we have kind of energy buckets that kind of describe the general positions of these types of molecular orbitals, where lowest energy is sigma, then pi, then non-bonding or like atomic orbitals, pi star, and sigma star. Those are the general camps, and this is just an order you need to memorize. Again, there's a lot of memorization here early on with just kind of like the basic order of things, and it's listed on the things to memorize on page 1. 1 second. But within each of these buckets, that's when the low energy trifecta is going to determine things. So, like if we're comparing a sigma CC and a sigma CO, we would say, okay, we're within the same sigma bucket, so we would look at electronegativity. O is more electronegative than C, so sigma CO is lower in energy. And when we are doing that with electronegativity, it's summative. It's not about polarity. So like if I had a sigma ON, I would say, okay, both of these are more electronegative than CC, so it's got to be lower than that. And then here, we have an O in common, and then we're comparing N and C. So which is more electronegative between N and C? Between nitrogen and carbon, which atom or which element is more electronegative? Nitrogen. So we would put the sigma ON or NO, it doesn't matter which way you write it, even lower. Because it's about the sums of those electronegativities, not about the difference between those electronegativity values. Yes?
So if it was like 2 O's, the sigma
Yes. Great. I need to go into practice, and then when we do more individual practice, I can answer some more individual questions. Last thing, a common mistake is symmetry. So these buckets, like sigma lowest, sigma star highest, that's symmetric, but inside the buckets is not symmetric. So like here, the sigma CO is our lowest energy, like molecular orbital in our diagram, but sigma star CO is not our highest energy one. So a lot of people, if they had like 2, 1 on the bottom, they would want to make it completely symmetric and do 2, 1 on the top, and that is a -1 on the test. You need to have the same kind of electronegativity dominating the rules on both the top and the bottom here. Does that idea of like, yes, there is some symmetry, but it's not 100% symmetric make sense? Okay. So, I sometimes do this to save space on a document and to make sure that you have kind of compact review sheets. I make a like practice handout, and that's like the last page of the section notes usually. So let's hop over there really quick. And what I've done is I've listed out the straight up just steps for drawing molecular orbital diagrams, because one page on your 9-page exam in 13 days is just going to be do an MO diagram. So you're going to do like 4 or 5 for homework. You're going to do some of the practice exams. You're going to do it so many times that hopefully it'll become a quick skill that those will be easy points on the test. But right now it's new, so I'm going to do it with you. And I'm going to do it with formaldehyde here. And I don't think that this one's explicitly in the problem set, and I just chose it because it's small. So I'm going to very rapid fire do all the steps and kind of talk through it, and then have y'all do one, and that's where I will answer a bunch of questions, okay? So, start off, first step, draw the Lewis structure. CO, H, there's some lone pairs. I did that very quick. It might take you a little bit longer, but typically for a lot of these, we will give you Lewis structures, so you don't even need to think about that. Second thing is count the valence electrons. So valence electrons, we have 6 from oxygen, we have 4 from carbon, and we have 2, 1 from each hydrogen. So that should be 12 valence electrons. Second thing is count your atomic orbitals. So that's the formula we did in the key idea number 1. So we have 2 hydrogens, so each of those have 1 orbital that they're contributing each. And then we have 2 non-hydrogen things. Each of those are contributing 4 orbitals. So we have 2 plus 2 times 4, which is 8. So in total, we should have 10 atomic orbitals. Great, we've done kind of our prep work. So now, the next step is to list out all of the molecular orbitals. And this is the order I go in. I start off with bonds, because you can see the bonds. So we have 2 sigma CHs, 1 sigma CO, and 1 pi CO. So I've listed the bonds. Part 2, I list the antibonds, because I can just really copy it from right before. So sigma star CH, 1 sigma star CO, 1 pi star CO. Okay, if I count this up, I have 2, 4, 6, 8. I have 8 molecular orbitals. But we know number of atomic orbitals, 10, equals the number of molecular orbitals, so I'm missing 2. Which 2 am I missing? Thank you, lone pairs. So we have 2 lone pairs in the oxygen. I like doing this, listing them all out as a separate step, because it kind of isolates it, and you're not worried about, as you think of each one, classifying it energy level-wise. You just kind of dump them all in one place, and then the next step is going to be to sort out the energy levels. So, what's our lowest energy bucket? A sigma, yeah. So we have sigma CH and sigma CO, which is lower in energy. Sigma CO, because it's more electronegative. Great. So we have sigma CO. Then we have the 2 sigma CHs. Our next bucket is the pi bucket, and we have a pi CO. Our next bucket is the non-bonding bucket, which is NO. Then we have the pi star. I know I'm going very quickly. Then we have the sigma star bucket. And so which is going to be lower in energy, the sigma star CH or the sigma star CO? CO, exactly. So sigma star CO, sigma star CH. So again, this is not exactly symmetric. Like you have 2 up top here and 1 at the bottom. Last step is we populate our diagram with our valence electrons. Well, we calculated at the beginning when we did our kind of mathy steps that we have 12 electrons. So we put 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And we have built an MO diagram. So this process, I know I went through very quickly, and like you shouldn't, even if you were like trying to write everything out, I don't think you would be able to write as fast as me because I'm like writing at the speed I'm speaking, and I speak very fast. But I want you to try out these steps, and the molecule here is H2NOH. It's on page 29 of the problem set, and I'm gonna leave the steps up here and write the H2NOH over here, and this is the molecule that you're gonna try to build an MO diagram for. So if you're a tablet user and want to zoom in, you can look at the steps up here and then be working on it. And I'll go around and answer some questions. Allison.
Yes. So it works. Can you explain again why it takes the C?
I didn't hear you.
Can you explain again why it takes the C?
So, two reasons. One is space and the other one's charge. So, it's attacking the pi star CO. And on the pi star CO, you have larger loads on the carbon, a less electronegative element. That's space. Second one is charge. The CO bond is polar, and you have a partial positive on carbon, partial negative on oxygen.
So there's a difference.
Exactly. Oh, now I'm getting confused with both Russell with A. Second letter? Agadia? Oh, good work. Agadia. Like go with you. Agadia. Yeah.
Question about a node. What is the actual definition?
A node is a place where electrons aren't.
Oh, okay.
Yeah, that's it. First letter? I want to say Molly. I know it's not Molly. So, I'm going to do something controversial, which is both not give you enough time to finish this, and also to not really go over it. And it's because this is a skill builder question, and you do have the access to the answers already. And I just wanted you to try practicing out some of these first steps. You shouldn't be done with your MO diagram, but you should have kind of like seen the adult walking and then tried to take your first little toddler steps of the MO diagram. And then you'll probably fall, but that's okay. You'll get right back up. You all learned how to walk. You all learned how to do an MO diagram. I will put up the answer later, but with that, quick question?
Yeah, what happens if you just have like one single electron? Is it like a lone pair then?
Like if you have an odd number of electrons, y'all won't do that. Yes, like it's called a radical, and like that's lecture 9. So later, yeah. And then quick question?
Yes, quick question. So the atomic orbitals, they don't need to match the number of sigma bonding and anti-bonding plus the number of pi bonding and anti-bonding. Like, okay, do you know how we listed them out right here?
Yeah.
We counted them, I counted them, and they ended up the same as the atomic orbitals. Are they supposed to match? Or is it
Yeah,
just-
because atomic orbitals equals molecular orbitals, and you just listed out the molecular orbitals.
But here, they don't match.
They
Like,
should.
with pi- yeah? Okay, I'll just check the answer.
Yeah, I'll put up the answer really quick, just so that you can see. But here, you should have gotten 11 atomic orbitals, and you would have the 2 sigma NH, 1 sigma NO, 1 sigma OH. So you have 4 bonds, 4 antibonds, and then 3 lone pairs. And so that's how we'll get there. And again, being controversial and a bad educator, I'm just not going to talk anymore about this and move on. So, let's talk now about an extension of molecular orbital theory, which is frontier molecular orbitals. And the frontier that we are at is the frontier of reactivity. So exciting. Great. Basically, we care about the orbitals that are the highest in energy and have electrons, and the orbitals that are lowest in energy and don't have electrons. And we give them specific names, and we call the highest occupied molecular orbital the HOMO, and we call the highest or lowest unoccupied molecular orbital the LUMO. Like saying all the words out is just a mouthful, so just say HOMO, LUMO. So HOMO and LUMO are labels that we give to designate something on an actual MO diagram. So like, for example, on this diagram that I just presented to you, you didn't see that. What is the highest occupied molecular orbital? The lone pair on the nitrogen. Good. So the HOMO would be this. And then the lowest unoccupied would then be what? Yeah, your LUMO here. And then right next door, I have another MO diagram, and let's just quick label the HOMO LUMO. What's the HOMO? And the LUMO? Yes. So when you have a full MO diagram, you are good to go with HOMO LUMO, and you can just see it there. But doing a whole MO diagram for every molecule you're ever going to work with in this class is just not feasible. So we are going to introduce some trends that help us identify things, orbitals that could potentially be our HOMO and LUMO. And like 90% of the time, the shortcut will work. So first up, how to spot a HOMO. First, HOMOs are good donors. So the best kind of donor that we can have, the highest energy of all these kind of filled electron buckets, are something in this like non-bonding bucket, right? 9 times out of 10, your donor is going to be a lone pair. So lone pairs are the great first option for a donor. The exception is halides. I won't get in too much right now why, but just know that there's an exception where halide lone pairs aren't as good donors. Again, sorry for not explaining. The second type of good donor that you should be aware of are alkenes, are pi-CC bonds, because let's say you didn't have any lone pairs, the next highest energy bucket that you have is a pi bucket, right? So a pi-CC would be a good donor. So 9 times out of 10, or actually I will say 9.5 times out of 10, your HOMO will be one of these. So if you were just looking at a molecule, let's say we look at this molecule, what would be a good donor on it? Yeah, a lone pair. And I could see someone saying a pi bond, sure, but this lone pair has a true negative charge. It wants to donate those electrons to become neutral. So lone pair of nitrogen is going to be probably our best donor. Great. So now let's talk about spotting LUMOs, or acceptor orbitals. So again, we go to our energy buckets, and we want the thing that is lowest in energy but unfilled. That's probably going to be in this non-bonding atomic orbital thing. But lone pairs are filled, so that's not going to be an option. So our only other thing that's really in this bucket are empty p orbitals. So these are typically going to be an empty p orbital on a carbon or an empty p orbital on a boron. So empty orbitals are typically our best options. Our second best option is we go one bucket up and a pi star. And it's typically going to be any pi star except for a pi star CC. The very quick explanation of it is a pi star CC is like this, where both of these kind of target orbitals would be kind of meh to attack, whereas a pi star CO has a clear good target, with one of them being bigger. And that's why a pi star CO is a really good acceptor, but a pi star CC is not as good of an acceptor. It can still happen, but yes. So you would pick the pi star.
Even though it's bonded, but like it's still an energy thing to see.
Yes, you would always break a pi bond before you would break a single bond. Yeah. And then if you don't even have any pi bonds and you don't have empty orbitals, then I guess we can put electrons into a sigma star, an antibonding orbital. Yeah. Michaela. That's a great question, and I don't have a quick answer. These are kind of like we're giving you a shortcut to doing a full MO diagram, and this is based on the trends of how molecules react. And so it's mostly that we want you to know this. I can give you a longer explanation after class, but for right now, I'm just going to say, go with it. So sorry. I know it's not helpful. But if we look for an acceptor orbital, what's a good acceptor orbital on this molecule? Say again? The central carbon, and what's the orbital? An empty, vacant, like p orbital. So we would just say like a 2p orbital on carbon. Great, cool. And then like this doesn't have any empty orbitals. It doesn't have any pi bonds, so no pi stars. So what's its best acceptor orbital that it could have? Sigma star, oxygen, hydrogen. So if you say an atom as an answer to what's the best orbital, that's just incomplete. We just don't have enough information. And if you say a orbital like sigma star, but you don't say both of the names of the partners, that's also just incomplete. And that's totally fine. Y'all are learning with us. So the sigma star OH is going to be a good acceptor here, or it's going to be one of the few acceptors we have. So these are terms talking about specific orbitals. Like a donor can be a HOMO, an acceptor can be the LUMO, and these are based on the MO diagram. Now let's kind of zoom out and talk about molecules. So in a reaction, the molecule that donates electrons, we call the nucleophile. So typically the HOMO is an orbital on the nucleophile. And then the molecule that accepts electrons is going to be called the electrophile. And typically the LUMO of the reaction is on the electrophile. We abbreviate them with NU and with EL or E for electrophile. I like EL, Tim likes E, so just you'll see both of them. And a specific type of nucleophile is a base. So an acid-base reaction, you'll spend a lot of time on that in Gen Chem, right? We use the Bronsted-Lowry definition for all of organic chemistry. And so an acid-base reaction is a reaction that transfers a hydrogen. It transfers a proton, right? So in an acid-base reaction, the nucleophile is a base. A base is a specific type of nucleophile. So do you remember that poll question yesterday that was kind of confusing? That was like, would you describe this as a nucleophile or a base or both? Well, the correct answer is both, technically. But if you have the option to call something a nucleophile or a base, and it is a base, call it the base, because it's a more specific name. So it's going to be better when you have an acid-base reaction to call it a base, even though it is a nucleophile. Similarly, an acid is a very specific type of electrophile, and it's the electrophile in an acid-base reaction. And so I have like a pictorial summary of this, of electrons flow from a donor, typically the HOMO, on the nucleophile molecule, and that whole molecule may be a base. And they go and flow to an acceptor orbital, which is probably the LUMO, and it's the LUMO on the whole molecule, which is an electrophile, and that electrophile may be an acid. That's a lot of information. Let's put it into practice with an example here. So this is from one of the skill builders, page 38, where basically it's asking you to draw some arrows and to identify like base, acid, or nucleophile electrophile. So the way that we're going to start this is first asking the question for each one, is the hydrogen the only thing that's transferred? So in this reaction, is hydrogen the only thing that's transferred between the two atoms? Yeah, so this is an acid-base reaction. So we know our label should be acid-base and not necessarily nucleophile electrophile, because acid-base are more specific. Second reaction listed here, is this only transferring a hydrogen? No. So we're going to label these like nucleophile electrophile. Third one, is the only thing that we're transferring a hydrogen? It is, but it looks wonky. Like it's a hydrogen, this hydrogen went from being attached to the left molecule to now being one of the hydrogens on H2O, but also there were some other changes. So because the main atom transferred between two things was a hydrogen, we would still call it an acid base. So that's step one, determining an acid-base reaction or nucleophile electrophile. Is that okay so far? I get like a nods or thumbs up or things. Okay, okay. Second question is we have to figure out what is the electron donor. So in Gen Chem, you're used to think about acids give up a hydrogen, right? That is not the way we're going to think about it in OChem. We're going to think about, okay, if an acid is going to give up a hydrogen, if something's going to come and take it, then it's accepting electrons from that OH bond and they're going on to the O. And so we could think of acids in this class as being electron acceptors. So between these molecules, one negative, one positive, which do you think is going to be the donor of electrons? The left or the right? The left. So this is going to be the donor, and the donor in the acid-base reaction is called what? The base. And remember, base is the specific type of nucleophile. So again, it's donating electrons, so it's a base. And then the other molecule is going to be our acid, because it's going to accept electrons. Okay, in the middle example, we know that our labels are going to be nucleophile and electrophile. And does this one on the left, does it seem like it's going to accept electrons or donate electrons? Accept as a positive charge, it wants electrons. So it's going to be the electrophile, and the other one's going to be the donor or nucleophile. Okay, last one is another acid base. So which one of these, left or right, looks like it wants to donate electrons? The right has a negative charge. So the donor in an acid base, electron donor, is a base. And that's a type of nucleophile. And the acceptor is acid. Okay, so we've identified the donors, acceptors. We have classified each of the reactions. Now we need to draw arrows and figure out what the specific orbitals are for each of these. So we said already, we did our classification, we said that this has a good donor of a lone pair of nitrogen. And then we also identified an acceptor orbital over here. But let's look. Did any bonds break over here? What bond broke? The sigma OH. And so if we broke a sigma OH bond, we need to put electrons in the antibonding orbital. Because electrons in antibonds. We're going to try that one more time because I'm going to need more energy. Electrons in antibonds. Make the bonds break, but that's close enough. It's organic chemistry. I can only ask so much. So we're going to put electrons from this lone pair of the nitrogen into the antibonding OH bond, and then that breaks the bond. And so we're going to take the electrons from the OH bond and put them on the oxygen. And then that represents this change. Again, the donor attacked the acceptor sigma star OH, and then it broke the bonds and the electrons went on the oxygen. Let's try the next one. So what's our probable donor on water here? So what's the best kind of donor that we first look for? Lone pair. Does it have a lone pair? Yes, it does. It has two. So we have a lone pair on oxygen. I'm going to put this over here. And so our donor lone pair on oxygen is going to attack the empty 2p orbital. So we draw an arrow to show that. And then that creates a bond. Now, did we have to break a bond here? No, we didn't put electrons in an antibonding orbital. So we're good. It's okay to just create a bond here if you didn't put electrons in an antibonding orbital. Then this one, what do you think is going to be the donor on OH? On OH here, what's going to be the donor? What's our best type of donor? Lone pair. So the donor on all of these, truly all of these, has been a lone pair. 90% of the time it's going to be a lone pair. So we have a lone pair on oxygen. And then what bond did we break? So you both are right. We broke a bond here and we broke a bond here. But let's start off with the acid base, the one that's just associated with the hydrogen. So we broke the sigma CH, didn't we? So that means we put electrons where? In the antibonding CH, yes. So we know because we broke the sigma CH that we put electrons in the antibonding orbital. So you would go arrow from a lone pair here into the hydrogen, and you're going to break that CH bond. And then we could have just, like the one above, put the electrons here. But where does it look like those electrons went over here? Like, did we create a new bond? Yeah, we created a pi bond. So let's take the electrons from this sigma CH and make a pi bond. But hey, that wouldn't give this too many electrons, right? This carbon would have too many. So we also have to break a bond. What bond did we break? The pi CO bond we broke. Yes, we do. And we break it, and what orbital did we put electrons in to break the pi CO? The antibonding orbital, the pi star. I know it's kind of weird because we're like, antibonding, pi star, all the lames. I'm hoping that y'all are kind of thinking the right answer or along the right answer, even if we're kind of saying kind of mixed things. So we're putting electrons into that pi star CO, and that's breaking this pi bond. And so that's how we get there. Like this second pi bond here, that is a direct result of this arrow pushing the electrons in and making a pi bond. This negative charge here is a direct result of this arrow pushing the electrons up on the oxygen. And like this, I'll write it out because this is like OH, and then we have like a bond here. This bond between the O and H is a direct result of this arrow. So I like to say like actions have consequences here in the sense that like your arrows, the changes that they intend should be reflected in the products. Yeah. So, great question. For this example, we did. Let's really quick look at an example where we aren't given it. So, remember how we list out the HOMO and LUMO of these? I'm going to just write them out here for a recap for us. So in molecule A over here, we said the HOMO was a lone pair of nitrogen, and the LUMO was sigma star NO. And for molecule B, we said the HOMO was lone pair on chlorine, and LUMO is pi star CO. So we want to figure out how these two are going to react with each other, and we have their HOMO and LUMO. So now let's ask ourselves, which is going to be the better donor between these two? So if we have a lone pair on a nitrogen and a lone pair on chlorine, which one's going to be a better donor? I hear both. Let's go back to our good donor rules. Our good donor rules say lone pairs except for on halides. So the nitrogen's going to be a better donor. And that kind of goes against electronegativity things, right? So it's a little confusing, which is why we need to remember that's the exception. So the better donor here is the lone pair on the nitrogen, and then the kind of losing donor is the lone pair on the chlorine. And then between a sigma star and a pi star, which is lower in energy? Our buckets are sigma star, pi star, non-bonding, pi sigma. So the lower unoccupied one is going to be the pi star. Second. So the pi star is going to be a better acceptor. And Danny.
Sorry, what was that exception that you just said?
Lone pairs are good donors except for on halides, or halogens, or however you want to say it. So, yeah. So every molecule will have a HOMO and LUMO, but the HOMO of only one of them will be the kind of donor for a reaction.
So if there's no way to figure out if that molecule is going to be a HOMO or a LUMO, without doing the way that we did it?
So, like, the way to concretely do it is build full MO diagrams, but this is going to become a secondary skill, that you're going to be able to look at a molecule and have a really good guess as to what the donor is, the HOMO is, and like 9 times out of 10 it's going to be a lone pair. And so this is like something that will come with practice. Yeah. So let's see, overall, it looks like this has the better donor. So molecule A over here is probably going to be our nucleophile. It's going to be the one that overall does the donor in this interaction, and we're going to have the lone pair on nitrogen. And then overall, molecule B over here is going to be the electrophile, and we have the better acceptor of the pi star CO. So now we draw our arrow from our donor, like our best HOMO, to our best LUMO. And it's from the lone pair on the nitrogen to the pi star CO. And if we have to do this attack and put electrons into an antibonding orbital, what happens to the bond? Breaks. So we push up. So now this is the hard part of, like, you have to draw what the product is. And to do that, I'm going to draw everything I didn't touch. So, like, I know that we still have NH2 and we have an OH. But then this arrow right here is going to create a new bond between nitrogen and carbon. So I know that that is the product of that arrow. And then that carbon is going to have still the H and the Cl, and it's still going to have an O here. But we broke that double bond, right? And those electrons that were in the double bond now became a negative charge. So this arrow is reflected by this and the only having a single bond here. Boop, boop. And that is how our arrows are going to represent changes in molecular structure. So our product molecule looks like this, and then we have to check formal charges, like we know we have a negative charge there. And also this looks bad, so I'm just going to move that because this is just a single bond. This nitrogen is connected to 4 things, so what charge do we need on it? Positive. Good. That is the product. So you predicted how these two molecules would react without us telling you what the answer is. That's a hard skill to develop, and it's something that you're going to do a lot of practice on. Okay? I hate to do the second big pivot of the day, especially because this was so much, but can we at least back up and say, do you feel a little bit better about MO theory after talking through some of these? Or at least better than you did in lecture yesterday? Okay, cool. Work. Let's pivot to acids. So, you talked about a lot of different ways of talking about acids, and Gen Chem and you were doing like KAs and everything, we only care about pKs. So you just need to know the trend of a lower pKa is a stronger acid. Great. So when we say strong and weak, what do we really mean by that? So a strong acid, for example, is a reactive acid. And then something like a weak base is going to be a stable base. And so one of the kind of central ideas, and what I write on almost every acid and base question when I personally am working it out, is I write strong acid equals weak conjugate base as kind of like a tight abbreviation of a fact that I know is true. Strong acids have weak conjugate bases. Does that sound like a familiar fact from Gen Chem? Okay, work. So people have heard that sentence before. So it generally, for me, is hard to conceptualize things being more or less reactive, and I prefer thinking about which of them have more stable conjugate bases. So we're going to do some mental gymnastics, and it's going to feel that way of like, okay, we're bending over backwards and like translating it, but hopefully you'll see this when we do some examples. So we are going to do like a YouTube influencer, like boxing match, kind of like cage match, fight to the death of two molecules. And we want to determine which one's the stronger acid. So for our strategy here, and this, we're going to go through each of like the Cario little acronym, pre-med, what we're going to do first is we're going to write the conjugate base of each of these. So we're just going to remove a hydrogen. And then if we removed a hydrogen for this one on the right, then what charge do we need to have? I couldn't hear you. Minus, yes, on this one. Good. So now I'm going to look at these two bases. I'm going to ask which one is more stable? The one that's neutral or the one that has a charge? Neutral. So this one is the more stable or the weak conjugate base. And then I know weaker conjugate bases have stronger acids, or stronger conjugate acids. So the more acidic between this and this is going to be this, because it has the more stable conjugate base. Let's try another. Yeah, like if you have a charge, you are more reactive than something that doesn't have a charge, generally. Yes. Weak and stable are interchangeable here. Yeah, because weaker conjugate bases have stronger conjugate acids. Great. So now we remove the hydrogens from each one of these, and we're comparing O minus and N minus. Which one's more stable with a negative charge, nitrogen or oxygen? Oxygen. Why? It's more electronegative. So this one is the more stable weak conjugate base, so we know it has the stronger acid. And again, we can generalize this, and I have generalized it and phrased it as the more electronegative element wins. So here, this one wins is the most acidic here, but we're explaining it in terms of conjugate base stability. So this is for if we have elements that are in the same period or essentially the same row of the periodic table. We know we have C, N, O, F, so we can compare these via electronegativity. But we're in the same column, like O and S, we have to look at atomic radius. So let's look at this. So if we have an oxygen and a sulfur, which one's going to have the bigger atomic radius? Sulfur. It's further down on the periodic table, right? So the oxygen is kind of, everything's in this like 2 shell, like a quantum number 2 kind of shell. But then sulfur, everything's in this big sphere, like a 3 shell. So let's say you had to have a negative charge. Would you prefer to put the negative charge on a tiny sphere where it's very compact and like there's a lot of charge and a little bit of space? Or would you want to spread out that charge across a larger space to kind of give it a little bit more room? Spread it out. And so it's for that reason that this sulfur, how larger atomic radius, is more stable with a negative charge. So it's the weaker conjugate base. So the thiol is the stronger acid. So column. These are on the same column of the periodic table, so we use radius. Row, we use electronegativity.
So the radius trumps the electronegativity?
It just depends on where we're looking. Like, are we comparing them in the same column or the same row? And if it's neither, I'll get to that. Okay, next one, I'm just going to draw out the conjugate base. So, one of these can do resonance. Which one can? The left, right? So this is our neighbor rule of it looks sp3, it has a lone pair, and it's adjacent to a pi bond. So it can do resonance like this. And if we can spread out a positive charge, that's going to stabilize it. So this is our weaker conjugate base, and this is our stronger acid. Also, I am aware that we've hit 1:30. I started 3 minutes late, and so can I go 2 more minutes? That I did really quick. This I'm also going to do very quick. So just to kind of expose you to some of it. Resonance is like I'm going to spread out the electrons along all of these atoms and fully delocalize. But induction I like to describe as kind of like tugging on electrons. So if there is a negative charge right here, and I'm a fluorine, I'm really electronegative, I might just like tug on the electrons and say, yeah, I'm going to take a little bit. It's kind of like if you're sharing a blanket and like you're just kind of like nudging the blanket over a little bit. And that's going to spread out that negative charge a little bit. Now, do you think that that's going to help stabilize the negative charge if we spread it out a little bit? Yeah. Is it going to be as helpful in stabilizing as resonance? No, because resonance is like ride or die. We will take on this charge with you. Induction is just like, oh, I just want a little bit more. So we say that this is the more stable conjugate base, and this is the stronger acid. Last one has to do with, okay, what if we can't do anything else, and we're just comparing like an sp2 versus an sp. So when we are on this scale, and they're both the same shell, then what we care about is S character. So in an sp orbital, what percentage of that sp orbital is S? 50. It's 1 part S, 1 part P. So this is 50% S. And then for sp2, what's the percentage S character there? Yeah, it's like 33%, because it's 1 part S, 2 parts P. So it's like 1/3 of it is S. So why is S helpful? So remember atomic radius, how we said, okay, if we can go from this to this, that's more stabilizing to spread it out? Well, that's when we're going between whole like shells of electrons. But we're both of them are carbon, both of them are the same shell. Here, hugging the electrons a little bit tighter is actually a little bit more stabilizing, because you put the negative electrons next to the positive nucleus. And so more S character is going to hug those electrons just a little bit tighter, not a ton tighter, and that's going to be a little bit more stabilizing. So we say that the more S character is going to be more stable. So which is going to be more stable between the alkene here and the alkyne? Alkyne, the sp, it's 50% S, so this one's more stable, and this is the stronger acid. The last thing I will say is Cario is fine and dandy as like a tool and like a little thing to go to, but there are going to be cases that are not nice and easy to compare between, and that is why we are saying that you have to memorize this chart. Like, we need you to have context for what these pKa values mean, and I need, for when I say something has a pKa of -8, you to be like, oh shit, that's a stronger acid than like hydronium. Like, that needs to mean something, and right now when you're coming in, like, that doesn't mean anything yet. Or if I say something has a pKa of 20, yeah, you need to know that that's going to be a little bit higher than an alcohol, but lower than an alkyne. And it gives you kind of a relative placement for the reactivity of things. That is why we are asking you to memorize this information, and that is why, in addition to the functional groups and those shortcut rules of donors acceptors, this is the third thing that you need to memorize this weekend, and like make the flashcards and start drilling it. Because if you wait to memorize all of this stuff the night before exam, poof, woof, woof. Thank you for coming to section. That was a lot. I have copies of the printed extra challenge problems if you want it. It will also be on Canvas. We didn't get to everything today because I wanted to spend a little bit more time on MO theory, but I feel okay about that. I'll answer any questions that you have. Go forth, prosper, have a good weekend, and thank you for coming to section. Yes.